very much. So, disclaimer, we also do deep learning and we like it. We want to talk a little bit about our experience of transferring research results to real industrial applications. This is why we call the talk Beyond ImageNet. ImageNet is the academic area, and let's see what we can do on real-life use cases there and in things we learned there. So, does that work? It works. We will have three parts, and Oliver will be there for the middle part. I'll start with a small introduction, maybe just to frame it correctly. Who of you has an understanding how a convolutional neural network works? This is roughly half of it, so I will a little bit explain how it works. That helps us to get a feeling for what we've done in the use cases and then to collect some lessons learned. So to give you first a feeling of who's standing here, I am Thilo, Oliver will come after me. We are part of ZHW Data Lab, and in 2014 we decided we want to look a little bit deeper into that new, not so new, but new word, into the machine learning method called deep learning. Out of that grew a couple of projects, a couple of people totally dedicated to researching that tool and applying it to as diverse kinds of use cases as possible, so that we learn as much as possible about that method and why it works, how it works, where it works, and what can be improved. So that's basically the idea. There's some machines to do it, and lots of great partners from industry who are brave enough to try it out. To give you a background, why do we have that hype of deep learning? You probably have heard of the ImageNet competition that was created as an academic competition to benchmark different methods at Stanford University. And we see here it came out in 2010. The task is you have 1,000 classes, 1 million images, so roughly 1,000 images per class. The images look like that, and the task is to predict what is seen on the image. So like here, you have a tiger on it, obviously, and the task has been predict 5 labels of what is seen on the image, 5 classes, and if the correct one is among the top 5, that's good, accurate. If it is not among the top 5, not good. So that has been the task. And in 2010 we see best methods reached error as low as 30%. So 1/3 of the images has not the correct label within the top 5 predicted labels, and the worst is about 80% error. Like, this is not very good. And the spread is quite wide. And then something happened in 2012 where Alex Krzyzewski and colleagues for the first time applied a convolutional neural network, one sort of deep learning method, to the ImageNet task, and directly scored with half the error rate of the best competitor. And what then happened basically is what we call a paradigm shift, right? All the blue things are traditional methods that have been used before, and all the orange things are convolutional neural networks. So convolutional neural networks have been there before. They started to appear in research in the early 80s. And they have been widely applied also in the 90s, also in industry. But it took until 2012, and this event, you can trace it down to this event, that a larger audience somehow got note of it and said, oh, might be a cool idea, let's see what we can do with it. Everybody afterwards used deep learning. Read convolutional neural networks for image classification on that task. And it continues. I just put some numbers here. Human performance on that task, if you take human annotators, is with 5% errors. I mean, there are, among the 1,000 classes, there are a couple of dogs that really look like each other. One has more pointy ears and the other one more sole, but I cannot distinguish them. So this is why humans have 5% error here, and you see a lot of teams in the end have better scores. I'm not sure if we have to count the numbers completely here, but what we can say is computers learn to see somehow things on natural images. So this is where the hype comes from. This is one of the pictures you probably all saw. I'm not sure, and maybe half of you understood. This is how you usually draw a convolutional neural network in a diagram. So you have somehow an input layer, and then magic happens, and then you have an output layer. Input is an image, output is the final class, the classification, is it a tiger, some sort of dog, a container ship, whatever. And here is a visualization of what the network learns at different stages. You can somehow visualize that and get intuition into that thing that's so often incorrectly called a black box. What I like to propose to you today is to think of the thing as being built out of building blocks. That can be arranged in different ways to tackle different tasks. So, of course, we have an input and we have an output layer somehow, and the most simple, basic, foundational building blocks we can see in a convolutional neural network are what we would call a feature extractor, a thing that learns to draw out of an image features that are predictive for the classes you want to classify into. And afterwards, a classifier. If you compare that to more traditional machine learning, this is what you would have done by hand, by your knowledge, by decades of study, what is a good feature in an image, and you would just put it in to a classifier. What you do with deep learning, that's the usual story like it is told, you also learn the feature extraction, and the cool thing is you learn the features that are really relevant for the task you're training for. So, and this might be different features for different tasks. Makes sense, right? For example, I worked a lot on audio processing, and when I did it in my PhD, early 2000s, we used the same features for almost every task at the end. And that already then didn't sound too good. So here we can learn features. If we stick with the metaphor of building blocks, let's go to the micro level, the very smallest building blocks we have in a neural network. That could be the layers of the network. For example, convolutional layers that are very good at finding local structure in the connectivity of the data. What is this in an image? The correlation of pixels in a very local area, which is a very good thing to do with images. We heard in the talk before that you have to give your network knowledge about what you know is true about the data in order to kickstart learning. And you do it in a CNN when you know when you apply to natural images, you know pixels that are close to each other are relevant for knowing what is in the neighboring pixels. The pixel that is on the complete other end of the image has not so much relevancy for the pixel here. So by taking layers that incorporate that knowledge of local things somehow are predictive for each other, we give the network prior knowledge so that learning gets easier. But we not only have convolutional layers, we also have, for example, recurrent layers, which have the hard-coded pre-knowledge of the temporal order of the things we feed them is relevant. So we can learn from the temporal order. This is, for example, important if you do speech processing. If you do natural language processing, where the next letter is relevant for the letter before. So in images we have local 2D correlations. In other problems we have correlation over time. So when we see these kind of things in data, we can pick as micro building blocks the correct layers to do this. And we can do this not only in the feature extraction part here, we can also do it in the output. Of course, if we have a classification problem, we take an output layer that is good for classification. If we want to do something else, we want to do clustering, we take different output layers, different loss functions, and so forth. Let's look a little bit, I promised to explain how convolutional neural networks work. Let's take a little time to look into how does the convolutional layer work. The idea is the idea of filtering, and everybody who did some image processing somewhere in time probably knows how filtering and image processing works. You have an image and you have a filter. What is a filter? Basically, coefficients for a small neighborhood usually take 3 by 3 pixel area that you can slide over the image and that you convolute, that is where the name comes from, with the image. For example, this filter, if you start in the upper left corner of that image, multiply the pixels, the first three in that row, and first three columns, first three rows, you multiply these pixels with the coefficients in that matrix, sum them up, this gives the value of the upper left pixel here. And then you slide it over the image. This filter is designed by humans, by image processing experts, to be an edge detection filter, right? So the image that comes out is completely homogeneous, except for where sharp edges exist in the image. So this is why it's called an edge detector. Humans somehow came up with the idea, when we do this, slide this filter over the image, do the convolution, we get an image that only shows edges. And of course, this helps in detecting what is on an image. Convolutional neural networks pick up on this idea. You basically have the same filter. You see here, this is the input layer, blue here. This, the output, is the next layer, and every pixel in the next layer depends on the same convolution operation we saw here applied to all the locations in the image. Except that, what is now the difference? The coefficients are no more designed by humans, like they were here, like an expert giving the right coefficients for edge detection. The coefficients now are learned. Convolutional neural networks somehow, you can say, offer an architecture that an image can be filtered by arbitrary coefficients, do edge detection, blurring, median filtering, high-pass filtering, whatever, all kinds of what can be done with image filters. But what is done specifically is learned from your training data set, and the objective you give the network. And you have several layers building on top of each other, and what usually comes out if you visualize these filters in the result, that in the first layers, really something like edge detection is done. And the next layer that builds on top of it takes the results of the edge detections, like where are edges in my image, and combines it to simple shapes. And then in the next layer, simple shapes are combined to simple objects. In the next layer, simple objects may be combined to more sophisticated objects. And we can do it, the more layers, the more data we have, until in the end we can classify complex objects that in the network are decomposed into their components and finally into pixels. So this is what a convolutional neural network does. It does successive stages of filtering images, of producing more and more high-level abstract representations of the content, until at some stage a human can do it. We have macro building blocks as well. We can not only compose different kinds of layers, we can also compose different kinds of networks. This is what is currently done and explored in many areas. You can have a CNN that is good at one task, and on top of it build a recurrent neural network that can learn over time and attach to it memory, all kinds of interesting stuff. So currently neural network research tends towards how can we use these building blocks and arrange it in ways that are beneficial for certain tasks. Why does it work if the stuff is so old? It goes back to a paper from 1959 that basically says that mammals do it the same way with a hierarchy of abstract features. I just want to propose the idea to you that against common opinion, public opinion, not all of this project is just due to more hardware and more data. Of course, this is important, but there have been substantial algorithmic improvements which we apply in all our projects basically. And Oliver will now give us some overview on what kind of things we did.
Now I will show you a few projects we did in the area of deep learning, and maybe. Okay, that's my turn. Okay, so the first case study is really showing that deep learning also can be done on limited resources, and here on the very extreme case on a Raspberry Pi. It's a kind of a small toy problem where we have indoor images which we use for training and outdoor images, or predominantly outdoor images we use for testing. We also had a classical approach where we also combined deep learning with a classical approach of detecting the face. This was done with the Ira Jones face detector. and then we see the face and then do some pre-processing and we feed the stuff in the neural network. And the training is done on a graphic card, but the prediction is done on a Raspberry Pi. And here you see how this looks like. You see then images coming in. Actually, this guy, we have only one picture of it from indoors because he didn't show up, but maybe it's zoom a bit there. Now I promise now I have the outdoor images, and this thing was trained indoor. Okay, so this is the guy coming in. We detect the face of it. Of him, and then this is the detected face. We do a very little pre-processing, then we feed the stuff to a neural network to somehow show this neural network working, and then the output is a probability that this image belongs to now Martin, okay? And yeah, that's this thing, and it's running on a Raspberry Pi. From the performance, actually, it's faster than or if you look at the accuracy of the approach, there's a traditional approach we compared against it, it's called Fisher faces, and it has an accuracy of 96%, which is pretty high, but it needs a very clever pre-processing, an alignment of faces. If you drop this alignment, the accuracy will go down. If you do the same thing with the convolutional neural network, the convolutional neural network is translational invariant to a part of it, so that it makes sense, not completely, because the face is still like in this orientation, and it makes it, but it's somewhat invariant on translation, and we don't need to do a clever pre-processing, and we reach a higher accuracy with the classical approaches in only 1/5 of the time, because we don't need this pre-processing. We continue this thing. There's an Android implementation of this network, and there's also like bachelor thesis just having been finished, where this is being used to detect little animals in like photo traps, so to find out that this weasel is of that species. Okay, so that was the first thing, somehow boosting the myth that you need high-end hardware to do the prediction. The other thing is in kind of an ongoing case study where we use deep learning for with a company in a kind of an industrial setting. It's also kind of a medical application, but more on the medical research type. It's in the pharma industry. It's called high content screening. What high content screening happens is that you put certain drugs or potential drugs on little test tubes, and this is a magnification of such a test tube, and you want to see that the cells react in a particular way. And these are now different colorings of the cells, and a biologist would say, okay, this one is phenotype 1, or 0, this one is phenotype 1, so she can classify these different phenotypes. Okay, so far so good. So why do we need some deep learning in this? First of all, this is done at scale. What you just saw, this is just a magnification of one little test tube, and in a normal test tube, and this is called well, there are about 900 cells in such wells. These wells come on plates where we have like 384 wells on each plate, and in a very, very modern screen we have 20 plates, which is really the lower end. So altogether we have like 7 million cells which needs to be classified depending on which drug was given to them. This requires, of course, for an automatic approach. And this has been done, or this is done currently as follows. By the way, this is a slide from our industry partner, Gene Data AG in Basel. So the usual pipeline, what is done is the biologist produces images, and then together with a bioinformatician, they come up with features, how to classify the cells, how to extract features to detect the different phenotypes. Then there's a machine learning phase, and then at the very end, the result comes out. And actually this campaign, just the analysis of such a screening campaign, can last up to 3 months, so it's a quite tedious process. Okay, so with deep learning, I mean, it's all what you have to do actually is, in the very end, is to provide basic samples of like the different phenotypes, images of the different phenotypes, train a neural network, and then investigate the result. You can even help the biologist more by using, this is this is somehow the comparison. So this is the classical workflow where the bioinformatician came up with a clever algorithm extracting like features, and then you do a machine learning approach, like usually linear discriminant analysis works quite well, distinguishing these two different phenotypes, This traditional approach, the approach we propose is simply use the images of the detected cells, then do the feature extraction with the convolutional part of the neural network, and then do the classification with the fully connected part of the convolutional network. Okay, the performance is, here if you use this approach, is about the accuracy is about 85 to 87%, here the accuracy is about 92%. But it's even, the ease in the workflow which makes it so beneficial. Okay, we can even do more. This is just using the ImageNet, which was trained with cats and dogs. And if you feed in the cells in this ImageNet trained with cat and dogs, you can use the internals of the ImageNet, like what we did. We used a particular layer and fed it into a two-dimensional visualization, so that you can see that you have similar cells appearing in a similar position in 2D, and then you can annotate like batches of images very fast. Okay. You tell me how. Okay. Okay. So this is the final thing. It's a kind of an industry 4.0 application. If you have a very expensive hardware, for example, like a wind turbine or something, and you would like to know if this bearing is broken or something beforehand. So what you do, you put in a vibration sensor on this machinery. This vibration sensor, you measure like 10 seconds of signal every day or so, and then what you could do a Fourier transform of this signal, and then you could collect data, and at the very end the machine was broken. This is artificial data. But if you're really clever and if you really look close and maybe on a better projector, you will see the first hints of the data derivation coming here. So what we used, machine learning approach, we used this data as training, where we believed the machine was okay. Then we fed it into different things. One thing depicted here is a variational autoencoder, where we put in the signal and try if we could reproduce the signal, and we trained it on the part where the machine was okay. And then this is the derivation, how good we can predict the training set, and then when the condition changes, we see a very strong signal that now something is going wrong, and of course the fault is appearing, so we used it. Yeah, I think that's all of my case studies, and Tito also wants to show one, because not only a visionary guy, but also a hands-on guy sometimes.
Thank you. We're also using deep learning, in this case fully convolutional networks, to segment newspaper pages into the constituting articles. This we have done with a company that is based in Zurich, Argus Data Insights, and we are currently in the last phase of the project where our system is implemented and the processes there. Without going into too much detail, what we feed in are small-scale scans of newspaper pages, plus a post-processed output of the OCR, of an OCR system, and then we train a network that is not just a convolutional neural network that puts out a classification, but one that puts out a classification for the complete image, every pixel, at one time. So this is why you see here, image comes out, image goes in, and image comes out. And we see in the end, we are quite capable of segmenting such a page into this kind of segmentation map. This is a ground truth, so this works reasonably well. The error score that we have here still reports 22% of errors, but if you look really close, this and this, okay, we didn't separate here, this one. But here it works, here it also works. This is really helpful, otherwise it helps humans doing the task much faster. What did we learn from such applications? I promised in the beginning Beyond ImageNet, and I didn't just mean beyond the lab. I also mean beyond classification of natural images, because this is where deep learning is good, and that has been shown over and over again. So what did we do? We did learn here not to classify. Actually, we learn to detect novelties. We learn a normal state and then can raise a flag if something is abnormal, which is not classification because the other class is not defined. We did it without encoders. We had not much training data here. It's 400 samples to train the thing. 400 very high dimensional samples. How is our satisfaction with that? I mean, in the end, even the machine could do everything humans could do, but it couldn't do things humans weren't able to do. And we are somehow only medium satisfied with that project because we think there's still potential, we still could do better. So we will try again here. we did learn to segment things, which is again not just classification, it's drawing a segmentation mask, right? So this is something different than saying cat or dog. And we also had not much data. Fully 500 pages that were fully labeled and 5,000 pages that had maybe 1 or 2 labels on it. Are we satisfied here? Yeah, quite so. It's better than every other automated system we saw anywhere. And it is about 70% accurate in judgment of a human expert, which is quite reasonably well. What else did we do? Oliver showed it and we did it also on other kinds of data, like audio data, acoustic data. We learned to cluster data, which is, again, not classification. Clustering is doing into groups, but you don't know the groups in advance, right? So we learned, somehow we are not completely satisfied with it yet, but we learned how to group into unknown groups and how to use this to be able to faster label data in order to get more training data to build the next better model, which is really useful because what we frequently see when we work with different industries, with machine manufacturers, with business intelligence companies, with media houses, what we see is these companies come and say, we have a need, and we see technology is somehow ready, maybe we could attack it, but we haven't collected data for ages. So we only have a small data set. We don't have 1 million images. How can we start? So we usually have a small data problem, and I put a check mark in parentheses behind it. We were usually able to work with a smaller data set we have been provided by our industry partners by using things like transfer learning, by using a pre-trained network from the internet as a starting point for incorporating our knowledge and fine-tuning it with the data we have. This is something we will try out in a project that's just about to start, by using architectures that somehow adapt to the data you have there, that can be compressed later, so you have fewer parameters. Fewer parameters means you can estimate them more robustly with less data. The thing we use in every project, it's an always on, is to use data augmentation. In the previous talk we saw the thing like the network doesn't learn the rotation. It actually helps not only to be rotation invariant, to show the network images that are deteriorated in a normal way. You can imagine it like that. This is usually like I tell it to my students. We as humans, in the first 1 year, what do we do usually? We lie on our back and we're just watching and learning how the visual world functions, like it's 3D, objects can be occluded, all these kind of things. The mother is always the same if I look this way or that way. We have to teach it to the machine learning system too. I mean, for us it takes a year. So with data augmentation we can teach the system this kind of common sense knowledge about how vision works. And we can work with unlabeled data with the thing Oliver showed, how do clustering and then label bulks of data instead of single data points. And we can even do semi-supervised learning. These are the tricks we apply when we work not with big curated data sets. Other lessons learned. Usually, this is maybe disappointing, usually when you try any machine learning model, but it's especially true for deep learning models, on a new task that hasn't been tackled before by thousands of others, it doesn't work. Usually it doesn't work in the beginning. And this then doesn't mean that it doesn't work, it just means it doesn't work from the first start. So for us it's always important to have some good baseline, maybe from the published literature, a model that has been trained on a close enough task, and start from this architecture and slowly adapt, look into the data, see where are the errors, and start from there slowly. Sometimes it happens that you get an idea, write it down, program it, it works. We see it seldom. Often it's hard work. And the best thing is start with something that has been published, where you know it works, adapt it to your task, see if it still works, maybe first on a small and artificial data set, then go to the next one. And of course, we also heard in the talk before, you have to use a loss function that is adapted to your problem. Just using cross entropy because it's the most mentioned thing on Wikipedia or the deep learning book. It doesn't help. You have to have a loss function that, I mean, this is how you tell the network what it should learn. If you tell it should learn and you don't care what exactly it should learn, you shouldn't be surprised if it doesn't work. So these are a few of the things that we usually have to do, and debugging machine learning models, looking into what are the errors, where does the network look at, what does it listen to. You can visualize these things. You don't get it with the push of a button, but the methods are there. You can look into deep neural networks. They are not black boxes. It's just hard work to get it out, and we have to do that. So, conclusions. I think we have a solid technical foundation. By technical foundation, I not just mean the abstract method. I mean software frameworks like Keras, TensorFlow, stuff like that, and a growing base of use cases where you can draw from and adapt to your specific use case. That gives us good confidence that the thing is ready to apply. And the next point goes into the same direction. What we see is roughly 3 months between a publication on a major machine learning conference or on archive pre-publication, pre-conserver, to an application in one of our industry projects. So here we have an area where industrial application and research are really, really close. This is really interesting for us as researchers. It's really beneficial for the company partners because it's not 10 years, the distance between groundbreaking research results, new algorithms, more robust methods, and the thing that we work. What we also saw is that success on a non-classical, non-just classification of natural images use case needs lots of experimentation. We also saw that in the talk before. We need to experiment with different architectures, with things, and it needs experience. It usually doesn't work if we give a bachelor student the TensorFlow tutorial and leave him unsupervised and go back after 3 months. It needs some experience with the stuff to know where to look at. Yeah, these were, in a nutshell, the things we wanted to communicate. Thank you very much for your attendance.